Hey everyone. Our lesson today is going to be on light and specifically the reflection and refraction of light. One of those might sound newer than the other. Probably have more experience with reflection of light, and refraction of light may sound a little bit more like a uh, foreign word that you maybe have not dealt with before, but nevertheless have had at least some experience with, even if not realizing it fully. So to start here, light is a form of electromagnetic radiation, and our human eye can only perceive a really small fraction of that electromagnetic spectrum. And towards the end of this unit, we will touch briefly on the electromagnetic spectrum, but to this point, you guys have a fair amount of experience with that spectrum and what it contains. So, of the visible light portion of the spectrum, that's all our eyes can perceive. And that's only going to cover wavelengths of light from approximately 4 times 10 to the minus 7th to 7 times 10 to the minus 7th meters. And this is going to be colors ranging from violet to red, or from our shorter, more higher energy wavelength to the lower energy, longer wavelength red waves. And that's really all our eyes can perceive when it pertains to light. So a little bit about the speed of light. Now the speed of light in a vacuum, remember this is where we'd have no matter, nothing to slow a light ray down or light wave down. This value is pretty large. It's 3 times 10 to the 8th meters per second. And it's represented by the symbol lowercase c. Now this, again, is only in a vacuum. So if we have light moving in anything but a vacuum, its speed is not going to be 3 times 10 to the 8th meters per second. Now this is considered what we call the upper limit for the speed of any material body, meaning no object can travel faster than the speed of light. As I just mentioned, the speed of light in any medium that contains matter is always going to be less than c. Now the equation to find the speed of light is similar to one that we saw earlier. To find the velocity of a wave, we multiply the frequency times the wavelength. So to find the speed of light, it's simply the same thing. The frequency of the wave times the wavelength. And that'll give us our value for the speed of light, which we know as a velocity. On to ray diagrams. We talk a lot about rays, and the explanation of these are probably a little bit more than necessary. But we see on the little diagram to the right here that we have an incident ray, and it's represented by this straight line. We'll kind of break this down a little bit. They're used to indicate the direction of wave travel. So the ray is a straight line that's drawn at right angles to a wavefront and points in the direction of wave travel. So if we have a longitudinal wavefront here, parallel wavefronts moving from top to bottom on the page, or from source to an ear, we would show a ray perpendicular to this wavefront, something like that. Now the wavefront is running left to right. Those waves are running left to right as far as how we draw them, but the ray is drawn perpendicular to those parallel wavefronts, and that's showing the direction in which that, or those wavefronts, are traveling from the source, in this case, to the ear. So an incident ray which we see there, is a ray that originates in a medium and strikes a boundary or an interface. Let's say to make an adjustment there. It's not interference, but it strikes a boundary at an interface of that medium with another medium. So basically, this is saying down here that we have a mirror. So maybe on this side we have a mirror, and over here we have, maybe that mirror is mounted to a wall. Out here we would have, let's say, air. So the interface here, where this ray is interacting with, is with the mirror and the air. It's originating in the air and it's striking the boundary or interface of the mirror with the air. Now the reflected ray, we see this incident ray comes here, hits the mirror, and is reflected. Now a reflected ray is a ray that has rebounded from a boundary or interface. In this case, it rebounds off of the mirror and is reflected. Now a refracted ray, which we don't see on this particular diagram, is a ray that results from an incident ray entering a second medium of different optical density, meaning that the material that makes up those two different mediums have different densities, and therefore the wave is going to behave differently in those two mediums because of the different density. That wave of energy is trying to move through all the matter that makes up that particular medium, and it's going to behave differently. So incident, reflected, and refracted rays are going to form corresponding angles that are measured from a line called the normal, which we see here. And this normal is a line that's drawn perpendicular, I drew the right angle there in the diagram, to the barrier or to the interface between two media at the point where the ray strikes. So the ray strikes our mirror here, and at that point we can make a 90-degree angle, and that's where our normal is going to be. The normal forms a 90 with the boundary of our interface. The angle of incidence is the angle between, oddly enough, the incident ray and the normal to the surface point, or to the surface at the point where the ray strikes the surface. So the angle of incidence we see is represented by the little I there. So that's the angle to the normal at which the incident ray is coming into this boundary. And we see here that I equals R. So the angle of reflection given by the diagram here should equal the angle of incidence. So the ray rebounds from the surface at the angle of reflection, which is the angle between the reflected ray and the normal. And we tie these two together with the law of reflection, which states that the angle of incidence is equal to the angle of reflection, or the angle of incidence is equal to the angle of reflection. And that's what we see here in the diagram. The angle to the normal that this incident ray is coming in is equal to the angle to to the normal that the reflected ray has when it rebounds. Now, this law is valid for all types of waves, including in this case light or water, sound waves. We'll mostly be dealing with this in the form of light. But the reflection of sound waves, this is where you guys probably have some familiarity with this. This is echo. So when you hear an echo, you're hearing the reflection of sound waves off of some boundary. Now, parallel light rays that are incident on a smooth surface, you can consider this as a mirror, are going to be reflected, as long as the surface is smooth, they're going to be reflected parallel to each other because all the normals to the surface are parallel. And when a beam of parallel light strikes an irregular surface, the reflected rays are scattered in all directions. And this surface, the irregularities on the surface, are going to produce non-parallel normals, or normals that are kind of angled all around each other, which is giving this light a scattered look. Now, for those of you that are I'm going to try this, probably going to not look the greatest, but those of you that are going to be potentially buying a diamond ring someday, this is my version of a diamond ring, I'm going to leave it at that. When I bought mine, I feel I had some pretty good information on what makes a diamond a nice diamond, and there are a couple things that you're told to look at: cut color and clarity. Now, a lot of people will tell you that the color is what you want, and some people will tell you that, well, you want it to be a clear diamond. You don't want to look in the diamond and see a bunch of different black dots or other irregularities inside the diamond, which is true. But the information that I got was that the cut was the most important. And I'll tell you why. And after, let's see, several years, 6-7 years of experience now, 8 years with this ring, I would still hold this to be true. Now, the way that this was explained to me was that when a diamond is cut ideally, any light that enters the diamond from any angle enters the diamond and is scattered inside the diamond. But it always leaves the way it entered. So no matter how light's entering the diamond, it's moving around inside this prism and it's getting reflected back out. And this would be a reflected light ray. Why is it important? Well, to me, it's important because this means my wife's diamond is always going to sparkle. Any light that's entering the diamond, because it's cut ideally, and the angles and the shape of this diamond allows light to be reflected perfectly, no matter how dirty this ever gets, it always sparkles. And if you talk to somebody about their diamonds, you'll see that over time, as they get dirty, they don't sparkle. They certainly look nice, but they won't sparkle. An ideal cut diamond, no matter how dirty it is, will always sparkle because of the way it reflects light inside of the diamond. I always found that to be really interesting. Now, a little bit about refraction of light. So waves are going to travel at different speeds in different media. So it should make sense that if you have a light wave or a sound wave, if it tries to go into a different media, it should change. If you have your head underneath the water in a pool or in a lake, and somebody's trying to talk to you, it sounds different underneath the water than it does if you were out of the water. That's because those sound waves are traveling differently in the air than they are in the water. So when a wave's traveling from one media to another, the speed of the wave will change. It'll increase or decrease depending on the density of the medium. And then the direction of the wave will also change depending on how that incident ray is traveling, or the angle at which that incident ray strikes the boundary. Now, refraction itself is the change in direction of a wave due to a change in density at the boundary between two different media. The amount of a refraction, or the amount of refraction of a ray, let's see here. The amount of refraction of a ray is going to depend on the properties of the two media at the interface and is measured by the angle of refraction. The angle of refraction is the angle between a ray emerging from the interface of two media and the normal to that interface at the point where the ray emerges. And I'm going to show you a little example of this. So we'll take a look at reflection and refraction. And to start here, I'm going to make, so we have two different boundaries. Right now we have air up here where we have our ray, let's call this a laser pointer. It's sitting here in air, and it's shining down towards an interface between the air and water. And I'm going to change this to air first. Now when I turn on this ray, and we can change this from a ray to a wave if we wanted. I'm going to keep this as a ray. And since we can call this a boundary. It looks like a boundary, but it's still air and air. So this is passing a light or a laser or ray through air. And you can see as we change the angle of this ray, the beam stays the same. When it crosses that boundary, it stays the same. And that's because the mediums here are the same. The density of air is going to be uniform between these two interfaces. Now, if we change this to, let's say, water, a couple things happen. Well, we have our normal line here, which is perpendicular to our interface. And we have what looks like two different rays. We have a reflected ray, which is being reflected off of this boundary. And we have one that is being refracted. It's trying to move from the air through the water, but because this ray from this laser pointer is traveling at a different speed in the air than it is in the water, we're seeing a little bit of a direction change. And depending on the angle, we can see that this angle changes. And when we line it straight up, straight down, there is no refraction. We do have some reflection here. It's lining up completely with the laser pointer. But depending on the angle of this ray entering the medium, we can see different refractions. The law of reflection states that this angle here is the same as this angle here. We can measure that. we can put this protractor here. Try and line this up the best I can with 0. And we'll put this ray at, let's say, 60 degrees. So an incident ray striking this boundary between air and water is being reflected at an angle of 60 degrees. And this is to the normal. And that's our law of reflection. A ray entering at 60 degrees is reflected at 60 degrees, or angle of incidence equals angle of reflection. Now the refraction angle down here is going to change depending on the medium itself or the angle at which this ray is entering. You see we can have a range from 0 to about maybe 49 degrees or so. And if this is completely horizontal, we're not going to have anything. But that does appear right just beneath about 50. So we have about a 50 degree range of refraction and a total of 90 degrees of reflection. Now if we change this medium, and we'll talk shortly about the index of refraction, but if we change this more towards air, we can see that the angle of refraction changes to the point where nothing's being reflected and nothing's being refracted because we have the same medium, air and air. But as we change this towards a medium that is more dense, like glass, we see much more refraction occurring at the boundary here between air and glass. And as we change this angle, now we see that we can range from 0 to about 39 degrees. So that range of refraction changes depending on the density, in this case, of the glass. And we'll get into exactly how we can figure out what these angles will be, the angles of refraction will be, depending on what mediums we're dealing with and how these rays are going to interact when doing so. More on that shortly. Hope you guys have a great day.